Well, hello, and here's another comp sci video for you. And this is actually I think the last day of a new topic in comp sci 2. So after today, you'll technically know every topic that was supposed to be taught in comp sci 2. And this is notes on searching. So get out a blank sheet of paper, label it notes, and your notes are on searching. Okay, so searching is kind of like sorting, but now let's say, okay, your methods are already, or your arrays are already filled. Now we want to look for where a certain element is. That's searching. And just like sorting, there's multiple different algorithms or ways to do that. With sorting, we had selection sort and insertion sort. There's other ones, and you'll learn about others if you take AP or any other computer science class in the future. But let's talk about two types of searching methods. The first one's probably the easiest. It's called linear search. And again, the goal is you're looking for an element in an array. Okay, so just as an example, let's say here's an array. We'll make it a fairly small one, 0 through 4. And 7, 2, 1, 9, 8. Okay, it doesn't have to be sorted. Let's say I want to know where is 1 in this array? Where's the first occurrence of 1? Well, it's at space 2. So my goal would be to go through what linear search would do. It would say, are you 1? No. Are you 1? No. Are you 1? Yup. So return this index. What if I was asking for where's 10 in the array? Well, it's not in here. So since I can't return an index value, what index value do you think it could return, or what value do you think it could return that would mean not in there? Yeah, something that could never be an index number. -1 is what we usually use. Okay, so if I said write a method that goes through an array and returns the position of the first occurrence of that element in the array, I think most of you could do that. It's a public int, because it's returning a position. It's called public int linear search. All right, so I'm going to have to give you an array, and I'm going to have to give you a specific value. This is a value that you're looking for. Let's write some pre and post conditions. Precondition is an integer array and a value. An integer array, let's be a little more specific, and a value to search for. And the post condition returns the position of the value or -1 if not in the array. Okay, so I'm going to go through the array, and I will use a for loop to do that. So for int I equals 0, I is less than a dot length, I plus plus, and every spot I just need to check, is the current spot equal to that value? So how would I do that? Right, I would just say if current spot A bracket I equals the value I'm looking for. And if you found it, what do you want to do? You want to stop and return that value right away. So you would return the spot you're at. So what would you return? You'd return I. Else you just want to keep looking for it. So else you just want to keep the code going. So you don't need an actual else statement. It'll just keep going without that. But if you get all the way outside the for loop and never found that, if that was never true, what do I want to do out here? Return -1. That's it. So linear search is pretty easy. It's easy to write, it's easy to do. The problem is if you have a million elements, it could potentially take a long time just to go one by one and looking for it. So the easiest is usually not the most efficient. And this one is not the most efficient. Remember what we used to talk about efficiency? Big O notation. So big O, for linear search, if I had n elements, so if you have n elements, worst case scenario, how long is it going to take you to find the value? Or how long is it going to take for this to run? Well, it's going to have to go n times. It's going to have to look, are you the number? 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 So for n elements, it might have to look at n elements. So linear search is O of n. Okay. So is there a more efficient method? Of course there is. More efficient method and the more efficient method is called binary search. Now, binary search is going to, worst case scenario, going to be a lot easier or a lot faster for the computer to run than linear search. It is a little more complicated. It also has a precondition that comes with it. So the precondition is that the array must be sorted low to high. Okay. The algorithm for binary search, so basically what it does is it checks the middle value. Rather than starting at the beginning of the array, it's going to check the middle value in the array. Then searches left or right. So picture an array. Okay, so the first, initially at least, the first spot's going to be your lowest value because again, remember it's already sorted. So the lowest value has to be here. The highest value has to be here. And the middle, well in this case, there's kind of a tie. So we'll just say this is the middle. Because you can't go between two values in an array. Got to pick something. It'll check this middle value. If that number is bigger than what I'm looking for, then that means the number I'm looking for has to be over to the left of it, or it's not here at all. If this number is smaller than the number I'm looking for, the number I'm looking for must be over here, or it's not in the array. But you can see why this might be more efficient. I don't have to check every single value if I do this. Every time I check the middle, I'm just cutting my array in half. So before I show you the code, let's do an example. Okay, so here's array A. And array A, I'm going to make it go from 0 to 5. So there's 6 elements in it. I'm going to fill it with 1, 3, 4, 5, 9, and 11. So my array is sorted. And let's say for my example, I'm going to be looking for a value of 2. Okay. So before the whole method starts, it's going to have to figure out where's my low, where's my middle, where's my high. So initially, the low value would be what? 1. Well, the value would be 1, right? The index would be 0. And the high index, where's the highest number? At 5. And for the middle number, again, I've got to kind of choose. So if this is low, this is high, the middle value is either 4 or 5. So think about how a computer would do this. If I do low plus high, so 0 plus 5 divided by 2, I'd have 5 divided by 2, which is 2.5 really, but the computer would say 2.5 is what? Lops off the decimal, it doesn't round it, it's just 2. So it would make this the middle value. So when there's a tie for the middle, you're going to go to the one to the left. So mid is at 2. Okay. So the first thing I'm going to do is I'm going to check, is the middle value equal to the value I'm looking for? So in other words, is 4 equal to 2? Obviously no. And the middle value is greater than 2. So if the middle value is greater than 2, that means I don't have to look at anything to the right of it because those are all going to be greater also. And all of a sudden, I only need to look right here. So what just happened? Well, now, low didn't change. Low is still at 0. High, the highest spot all of a sudden is 1. And if I did a new mid value, the middle between these two spots, you got to pick something. 0 plus 1 is 1. 1 divided by 2 is 0.5, but they would say 0. So mid is 0. So now this is low, this is high, and this is also mid. Okay, so now I do the process again. I'm going to check, is mid, is that equal to the value? Mid is 1. Is 1 equal to 2? No. 1 is less than 2. So if this number is lower, then that means I don't have to look at anything beneath it, which is good news because there's nothing beneath it. I'd only have to look at stuff to the right of it. So this is the only place where my value could be now. So low is going to change. Low isn't 0 anymore. Low is now space 1. High is still space 1. What do you think mid would be? Mid would have to be 1 also. They're all 1 because 1 plus 1 is 2 divided by 2 is still 1. Do the process over again. Is the middle spot equal to the value? Well, Well, again, now this is low, mid, and high. Middle spot is 3. That's not equal to the value, which is 2. So no. 3 is bigger than the value I wanted. So anytime it's bigger, I got to go to the left, but there is nothing to the left. So what's that mean? Value is not in the array. Okay, so what just happened was it took me 3 tries. I checked 3 different values to figure out if 2 was in the array. So it's definitely more efficient than linear search, because linear search would have had to check all 6 values before it told me that 2 wasn't there. But obviously the process is a little trickier. Let's see if we can write this into code. So we're going to do public int binary search. And I'm going to send it an array. I'm going to send it a value to look for, just like linear search. So this time there is a little bit more to the precondition. It can't just be any integer array. It's a sorted integer array. This only works if the array is sorted. And a value. Post condition returns position of value. This is the same as linear search. The result should be the same. Returns position of value or -1 if not in array. Okay. Now if we use this example, I think we can figure out how to write the code. Before I started going through this process, I had to set a low, middle, and a high. Low is easy. That's always going to be the first space in the array, which is always 0. High in my example was 5, but if it was any length, how could I get what goes for the high? It'd be a.length minus 1, because this is a length of 6, but the index is 5. So we're going to set int low equal to 0, int high equal to a.length minus 1. And how was I finding mid every time? Well, I was just taking whatever my low value was plus my high value and dividing it by 2. It's integer division. So low plus high divided by 2. All right, so I got my low, high, and mid set. Now, these are questions that keep happening the same. I'm always checking, is the middle value equal to the value I'm searching for? And if not, I adjust low, middle, and high. So I don't know how many times these are going to happen, but I know that they're going to happen multiple times. What kind of loop do I use if I don't know how long it's going to happen, but I know I'm going to do it many times? Hopefully you're thinking while loop. And I'm going to leave the condition empty for now. We'll fill that in at the end. Okay. The first thing I check every time is the middle value I'm looking for equal to the value in the array? So is the spot at the middle value, is a bracket mid equal to the value I'm looking for? So if A bracket mid equals value. Well, if I've found the value, that's great. What do I do? That never happened in my example, but if I did find it, what would I want to do? I want to return the position of that value, which is mid. So we would just say return mid, and we'd be done. Great. What if it's not? Well, we saw instances of that. In this first case, the middle value was greater than the one I was looking for. So else if A bracket mid, if that's greater than the value I'm looking for, what changed? When it was greater, that means that everything to the left of it was what I could search for. So low didn't change, low was still 0. High changed, and it changed to 1 less than what the mid value was. If this was mid initially, now I only have to search over here, so high became 1 less than what mid was. Okay, so what am I doing? Sorry. You would set high, the new high, is equal to 1 less than what mid was. And what else changed? Well, mid changed. And again, I always find mid by doing low plus high divided by 2. So let's get a new mid value. Low plus high divided by 2. Okay, now there's only one other case. So I'm just going to call this else, but really it means else if the middle value is less than what I'm looking for. So that happened here when the middle value was less than what I was looking for. If the middle value is less, then I only have to search to the right of it. So high didn't change, low did. And low became 1 more than what the old mid value was. So low equals mid plus 1. And again, I got to get a new mid value also. Low plus high divided by 2. And that's all I need inside this while loop, because then it's going to go back and check for the next time. Okay, now I have a new mid value, and I'm going to search again. Outside the while loop, so if you get through everything like we did, and then there was at one point nothing left, we return -1. Okay, so all we need to do is figure out what condition goes in here to tell me that something went wrong and there's nothing left. So let's look at this last one again. When low, mid, and high were all 1, technically the number I was looking for was greater than 2. So anytime it's greater than, what should happen? Well, if it's greater than, high equals mid minus 1. So high would have changed, or low would not have changed. Low would still be 1. High would have changed to mid minus 1. And since mid was 0, or sorry, since mid was 1, 1 minus 1 is 0. And look what just happened. Does that make sense? Can low be 1 and high be 0? No. When low and high kind of crisscross over each other, that means you've gone too far. There was nothing to the left. So the condition that I'm going to fill in here, you can keep running this as long as low is less than or equal to high. You want to stop it as soon as those crisscross over each other. Okay? All right, so that's a binary search. Let's do a couple more types of questions you could see on a test for binary search. So given this matrix, here's matrix A again. And I'm going to make it length 6 again, just like the last one. And let's do, oh, I don't know, 3, 2, oh, can't do that. Here, let's just use the same example we did last time. 1, 3, 4, 5, 9, 11. Two questions. First one, let's say we're looking for a value of 10. So looking for value equal to 10. What is the search interval? After the first pass through the while loop. So obviously initially we've got the whole matrix or the whole array to search through. But after I go through the while loop one time, what am I looking for? Basically, am I looking to the right of the middle or to the left of the middle? So remember, before that while loop starts, if you go back to that code real quick, before it starts, we set initially low, middle, and high. So initially, what would low be? It'd be at space 0. What would high be? Where would high be? It'd be at space 5. And where would mid be? Low plus high divided by 2. 2.5 is 2 in comp sci land. So we've got low, we've got high, we've got mid. So after that first pass through the while loop is saying, okay, after this while loop happens one time, what's low, mid, and high? So it's going to check if it's equal to the value, and then it's going to adjust low or high based off of how mid compares to the value. So after the first pass through the while loop, it's going to check, is a bracket 2 equal to 10? Well, a bracket 2 is 4. 4 is less than 10. So since 4 is less than 10, that means I must be to the right of it if I'm in there at all. So if you notice, high hasn't changed. High is still at space 5, but the lowest value I could search for now is at space 3. So after one pass through the while loop, you're going to search from a bracket 3 to a bracket 5. And that's the answer. Okay, there's that one. Okay, second question, same array. Now I want to know how many passes through the while loop. To determine that 10 is not in the list. Okay, so this first setting of low, high, and mid isn't in the while loop, so that doesn't count. We've already done one pass through. So let's just rewrite this quick. We started with low being 0, high being 5, and mid being 2. After one pass through the while loop, low was 3, high stayed 5. What would mid be? What's the middle between 3 and 5? 4, obviously. So mid is 4. So after one pass through the while loop, I'm looking just at this blue section. And I would check mid again. So I'm looking for 10. 9 is less than 10. So if I'm less than 10, if this is lower, that means I don't have to search over on this side. I'd have to search right here. So low and mid and high would all be 5. So the second pass through the while loop, low is 5, high is 5, and mid will also be 5. Now it will still have to go through the while loop one more time to check if 11 is equal to 10. It's obviously not. I need to go look over here. So the third time through, if I'm looking to the left of it, it's high that's changing. My high would now be 4. Low would stay 5, and that's a problem. So this is where it returns -1. And my answer, how many times through the while loop, was 3. Okay, so those are the types of questions you could get asked for on a multiple choice test with binary search. Last thing, let's talk about Big O. For n elements, binary search is well, let's see. Linear search was O of n because I had to look through every element. Binary search, it keeps cutting in half. It's not just half n because it's even less than that because it doesn't check everything after it cuts it in half the first time. It keeps cutting it in half. The thing to remember with Big O is that you're cutting in half each time. So for example, let's say you were starting with 1,000 elements. And let's talk worst case scenario. So if I get all the way through and never find it, I have to search through everything. So initially I have 1,000 elements to look for. That's going to get cut in half after I look at the middle value. Now I only have 500 elements to look for. That gets cut in half again. Now I only have 250. Cut in half again, 125. Now cut in half again, you get like 62.5. We'll just call it 62. Cut in half again would be 31. Then cut in half will give you 15.5. We'll call it 15. And there'd be 7, 3, 1. And then after I've searched that last one element, I'm done. So how many times was that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 1,000 elements only took me 10 times. Essentially, I got to know how many times do I need to double it to get to the number of elements I have. 2 to what power would give me that element. And if I wanted to solve for x here, here's where it gets a little mathy. Some of you may have heard of this in your math class, some of you may not have. How would I get rid of the 2? If I need to solve for an exponent, you're taking the log of both sides. Okay, so we say that Big O for binary search is Big O of log n. And that's way more efficient than O of n. O of n, linear search, if you had like y equals n, you'd have a linear graph, which grows fairly quickly if n is a huge number. Log graphs look something like this. It starts by growing quickly, but then levels off. So for a lot of elements, log n is a lot smaller than O of n would be. Okay? So again, binary or Big O notation, a little tricky, but that's all you have to worry about this year is that binary search is more efficient. And anytime it cuts in half, it's got that log n efficiency. All right, that's all I got.